Thanks to Chip Pankow and the whole RoboRace team for allowing SAE Southern California to come visit your new shop. I must say it looks pretty cool. Glad that we have a good audience tonight. I think we've got a really interesting subject matter. So just maybe a few quick things about SAE Southern California before we get into the really interesting stuff. So SAE Southern California is a group of volunteers, professionals in the industry that are led by a board of directors, some of whom are here tonight, like Dean Case and others. But we try to put on really interesting events that are of professional value to people such as yourselves. So we do it roughly on a monthly basis, and we have a good time doing it. It's a lot of work, but we get to have things like this happen when you grant us access and we learn about all this cool technology. So, fun time. If you are interested in getting more involved in SAE Southern California, we're happy to have you. We're always looking for active volunteers to help out put on really interesting content. So, after the event, if you're interested in learning more about that, you can come talk to myself, you can talk to Dean Case. So again, we're happy to have you if you'd like to join us. Maybe just a few bits of housekeeping before we begin. This weekend, we have our annual student workshop at El Camino College down in Torrance. Starts at 9 a.m. So if you are interested in, if you're interested in getting a job, this is a good place to find connections within the industry and learn how to market yourself as a young engineer. So if there are any students in here that are interested in that, 9 a.m. El Camino College. On Monday, we also have our board of directors meeting, which is a monthly occurrence, and we do that at Motivo Engineering in the Torrance area, South Bay. Again, if you're interested in attending or learning more or becoming more active, we can hook you up with that as well. So that's all I have to say at the moment, but we'll get to the good stuff now. I'll let Austin kick us off and introduce RoboRace.
Hi there, everybody. My name is Austin Esau. I'm an engineer at Motivo Engineering. The SAE meetings like this are really fun. We do them every month. I help organize this along with a ton of other people that we couldn't have done it without lots of volunteers. So the coolest thing about SAE is being able to put on meetings like this. So if there's any place that you see, oh wow, they make this really cool thing, they do this really cool stuff, I would love to go check it out. You can volunteer with SAE to put on a meeting like this, and you get kind of the inside scoop and get to see a lot of stuff, get to see presentations from people that normally you might not be able to go see. But if you say you're with SAE, then it's like an open invitation to go talk to anyone you want to. So here we're at RoboRace, and I'm excited to see what we have. We got some great presentations. And first, the Chief Championship Officer, Chip Pankow, over here. And he'll give us a presentation. So thank you so much for coming.
Thank you very much. And first of all, thank you to SAE for bringing this opportunity to us. The great turnout, really happy to see it. And welcome to our new home in the USA. RoboRace started about 3.5 years ago, based out of the UK. Yeah, is that better? I'll stand away from it a little bit. And this is Los Angeles headquarters, and I'll tell you a little bit about our global presence. So I want to cover a few things. The first one is really what is RoboRace? And then this evening we have a few presentations for you. We'll go through trackside engineering with Matt Smith, and then we'll have a short break, get some refreshments, and maybe we can ask a few questions just informally out in the crowd, and then we'll come back and we'll talk about RoboRace sim and software development with the Hive team. Nikita is going to kick that off, and then at the end we'll do Q&A. So if you could save your questions till the end, that would be great. Yeah, my name is Chip Pankow. I'm the Chief Championship Officer of RoboRace, and my responsibility is to really make sure that the competition happens within RoboRace. RoboRace is just that. It's a competition for AIs. Hold on a second. Okay. It's a competition. Okay.
Thank you, Microsoft.
There we go. It's a competition for AIs. And essentially, RoboRace provides the platform. So when I say platform, what do I mean? Well, it's the cars, of course. But then in addition to that, it's the racetrack. It's the competition structure. It's the media that goes around it. And ultimately, it's the audience. And why do we do all this? What's the goal of it? And the goal for us at RoboRace is to bring autonomous to the masses. Educate the masses about autonomous. We all know autonomous is coming. We can all discuss what the time frame of that is. But we want to educate. We want to demystify what is autonomous and what is an autonomous driving system. What is it and how does it work? And then we also want to have competitions. So the early pioneers here that have their software stacks, they can see how they stack up against their competitors. So we have competitions that do that. Because of that, we're always evolving our type of competition. And we'll talk a little bit about the different types of competitions that we have. Matt will give you a couple examples when he's talking of different types of competitions where we have multiple cars, we have single cars. Sometimes we're looking for outright performance. How fast can the car go on the track? Sometimes we're looking for precision. Sometimes we're trying to figure out how well the car will localize. How well does it know precisely where it is in the world? So these are all the different things that we do with our different competition structures. And we get the question a lot, who are the teams? And essentially we have two types of teams. We have university teams, and these are universities. They come out, they're doing research on autonomous, and we have 3 university teams that are running with us right now. And then we also have some commercial teams, and it's their business to create an autonomous software stack. And they compete against each other. It's all equal footing. Again, we're providing the platform, we provide the cars, they load on their software stack, and then we put a competition in front of them, and we see how they do at the end of the day. So rather than my going into a long dissertation about what does a race look like, I've got about 90 seconds video that we're going to look at. And this video is from April of 2019. It is the first autonomous race that we had. Multiple vehicles, overtakes. Again, Matt's going to give you more detail on what that looks like. But hopefully this gives you a little bit of idea of the flavor of what we're doing, the vehicles that we use, and the process that we use to get there.
That's right.
So following that up, we did another 5 races. We finished up and did our last race of season alpha in November in France, and had a good competition. So right now the teams are back and we're working on the competition structures for season beta. 2020 will be our season beta championship. And then that prepares us for season 1, which will launch in 2021. Just a few more things about RoboRace. Some base locations, London and Los Angeles, our campus here. And then in addition to that, we have test and operation facilities in Millbrook in the UK, at the Proving Ground, and then in Las Vegas at Las Vegas Motor Speedway. So in each one of those locations, we're doing about 100 days of on-track testing per year, to working with the teams, working with the cars, working with the platform to develop and evolve it. So to tell you a little bit more about those areas, we've kind of decided to divide up the presentations into the real world, and this is what Matt deals with on a day-to-day basis, being one of our senior trackside engineer for RoboRace. So he's dealing with the car, making sure it works, make sure that the software is integrated properly with the car, always monitoring what's happening on the track with the car, and learning. Every time we go onto the track, we're usually trying something new, and we always try to learn from what we do, so we're constantly improving. We're also helping the teams to improve, and we're always learning from them. So Matt will tell you a little bit about that, and then we'll take a short break. And then after that, Nikita will come up, and Nikita is from Hive, and Hive is our internal simulation team. And as we looked at autonomous driving, it became obvious relatively quickly that we needed better simulation software. There wasn't really anything that was available off the shelf, so we have a group of engineers that are based here that are working on that simulation software that's specific to the task that we're doing. So Nikita will give you an overview of that software, and then we'll take questions. So, Matt, take it away.
Thanks, Chip. So as Chip said, my name is Matt Smith. I'm a senior trackside controls and systems engineer. I'm now based at the Las Vegas center that we have, but I used to be working out of the UK center, which is now Millbrook, which is in Bedfordshire. So I just wanted to give you guys an overview of what my responsibilities are when we take a car to a track. So we often go to many different locations. Often one week we're in one location, next week we're in a different location. So making sure that we have a robust system which works everywhere that we go is what my job is essentially. So bit of my background: before I joined RoboRace, I was at university for 5 years doing a master's degree in mechanical engineering, and then during that time I was also part of Formula Student, which I think you guys call Formula SAE over here. I did that for 5 years. I was part of a suspension team, and then I moved over to the more system side, and then that kind of allowed me to get this role here at RoboRace, which I've been doing for about 2 years now as a systems engineer. So I wanted to show you quickly our two cars. This is our DevBot version 2.0, which is a rear-wheel drive vehicle, an iteration of our first DevBot, which was an all-wheel drive. This car is about 1,200 kilos, which is 2,500 pounds, something like that. It's rear-wheel drive, individual motor to each rear wheel, providing 135 kilowatts of power per wheel. And then we have the Robocar, which is our more custom-made car. This one is fully autonomous. There's no room for a passenger like there is in this one. This one's all-wheel drive. It has double the power, double the motors. But this is the car that I want to focus on today for the presentation. So I just want to kind of let you guys know how complex these cars are. They don't look too much from the outside, but under all that bodywork, there's about 30 different control systems. And my role is to make sure that firstly they're configured correctly, they're all communicating to each other correctly, and that ultimately they are capable as a whole package of ensuring that that car can drive safely, fast, and produce everything that we need it to. So normally when we go to a track, this is what my home becomes for about a week, and I sit there for 10 hours a day in front of those screens. It might not look like much, but everything that we need is on those 4 screens there. So we have on the top, we have main ECU telemetry, which is the heart of the car is sending us every, I don't know, maybe 0.01 of a second. We're getting 1,500 new data points, and we're relaying that constantly every time we run the car. And my job is to monitor that and ensure that everything that we're seeing is showing that the car is healthy and it's performing as we're expecting it to. We also are capable of tuning and controlling our vehicles from our race control center. So from that desk there, when the cars are out on track, we can make some adjustments to them, control them, stop them, which is super critical. And then, as I said, track monitoring and flagging on the left-hand side there. You can see a track layout, and that shows us at all times where cars are on track, what they are doing, and that allows us to safely monitor what's going on track. And then lastly, there's a little red button there just over my left shoulder. That's our emergency stop system. So if anything goes wrong, that gets smacked and the car comes to a pretty abrupt stop. So those are the kind of 4 areas that I'm focusing on when I'm trackside, and that is anytime a car is out on track, all of those things need to be happening. So it's pretty intense when you're there to make sure that you've got an eye on as many things as you can have and that the cars are working as you're expecting them to. So I wanted to focus on 2 events that we've done. I could go on for ages, but we have 2 events that really kind of stand out for RoboRace in 2019. The first one is what Chip talked about. This was the first round of Season Alpha that we did in Monteblanco in Spain. And the second one is the Goodwood Festival of Speed hill climb that we did in July last year. So firstly, I'm going to talk about Monteblanco. We spent a lot of time in the lead up to this event developing the DevBot that I showed you earlier. That was probably about 8 months of work. So this event in Spain was kind of the first time that we took that car out on track and kind of showed what it was capable of, proved to ourselves that all of the development work was a success and that we'd made a right decision in what we'd done. So that was a super critical thing for us. Previously in RoboRace, we have had cars on track having competitions against one another. We were in Berlin for the Formula E event in 2018, and we had 2 cars on track there, but that was a time trial. So we did, one car did a lap, came in, another car went out and did a lap. This was going to be the first time that we'd ever had 2 cars on track at the same time. And that was going to be a big step for us in terms of what we'd done in the history of RoboRace and also what we were capable of doing going forward. So we were happy with what we had done up until that point, but when we suggested the idea of having 2 cars on track at the same time, it raised some concerns for some people. So obviously we needed to make sure that we were going to be able to do that safely. So we created this piece of software which is called Car Control. And here we're able to constantly monitor everything that's going on critical to the autonomous systems on the car. So often we can always see the GPS data of the car, but the car is trying to localize itself for its autonomous systems. And so sometimes a car thinks it's in one place, but is actually in another place. And that's a really serious situation because if a car's trying to drive on a track and it thinks it's on track and it's not, then things can go wrong. So we spend a lot of time studying this data pre-event, post-event, and during the event to make sure that we are capable of hosting these events safely. But the most important feature on this software is the ability to control the cars at any time. So anytime a car goes out on track, with this piece of software, am able to do anything that I want to that car. So I can launch the car in autonomous mode, I can stop the car, I can slow it down, I can speed it up. This allows me to make sure that everything that we're doing is within tolerance, is within the spec of our test plan to make sure that we're not doing anything that we hadn't planned to do. And this piece of software is what really allowed us to have our Season Alpha event. So I just wanted to show you guys really what that came to. With our race control software, we're able to, not only am I able to see everything, the cars themselves are able to see everything. So any car that's on track can see the location and status of any other car on track. And that is what overall allowed us to take 2 cars, put them on a track and have them race each other and overtake each other. So I wanted to show you guys what that overtake looked like.
RoboRace.
So that was the first time that we ever completed a fully non-manipulated overtake. So often during testing, we'd want to test that the team's software was capable of doing an overtake, so we'd force it. So I would be able to control the speed of one car, force the other car to overtake. But this was the first time that we'd let two cars go. We'd just press go, and we let them do their thing. And the race happened, and we had an overtake in the race, and the team that started second won the race. So for us, that was a big achievement to develop that system and not only be able to make sure it worked in practice, but we put it in a race and it worked perfectly. So that was a big achievement for us. And that was our first event of the season. We had more throughout the year, and we were able to develop that even further. Okay, so the next event I want to talk about was the Goodwood Festival of Speed, which we did in July 2019. We went and had one goal, really, which was to set an official record for the first and fastest autonomous car to complete the hill climb. For those of you that don't know, Goodwood Festival of Speed is the world's largest motorsport garden party, I think is how they describe it. For us as a team, it's the most famous hill climb that we know of. We competed in it before, in 2018, 12 months prior, but we didn't set an official time, and that was with Robocar that we used last time, and this time we were going to use DevBot. But this time we were going there with the purpose of setting an official time that Goodwood would recognise for us to put out to the world, and hopefully someone can come and challenge that in the future. Hopefully beat it, and then we can beat it again, and we can keep going back and forth. So that was the goal. The goal was to go there and complete that. So often our team will say, we want to do this, and then we go, okay, great, but we don't really know how we're going to do it. So then we have months and months of planning to go away and try and make that happen. So that's what we did here. And from completing the event before, we knew that there were three things that were really going to make this event challenging for us. The first was timing. This is always the case when you go to a big public event. There's hundreds of thousands of people that go to these events, and you have a very, very small slot to be on track, and if you miss that, that's game over. So that is we always have to have a plan, a minute-by-minute plan, to ensure that we're going to be able to do that properly. The next one is GPS coverage. There isn't any, essentially. The whole run is covered in trees, which means that our GPS localization layer just doesn't work. We can't use it. So we had to use our LiDAR driver, and that presents a lot more problems going forward. I can show you a little bit later on. And the last one is that as much as we wouldn't like there to be, every day people crash going up this hill climb, which is bad enough as it is. But for us, it's pretty severe because it means that the track boundaries change every day. So the track boundaries are made up of hay bales. If you crash into them, they're never going to put them down in the same place again, which means every day what we had decided was our drivable area had changed. And if they had to put a hay bale half a foot closer in track, we could just drive into it, essentially. So for us, that was a risk that we had to mitigate as much as we could. So what did we do? Well, we needed to replicate Goodwood as best as we could. And Goodwood's pretty special, as in it's a long hill climb. It's pretty hard going up. There's a high gradient, and it's super narrow in places. And we wanted to be able to test in that sort of environment to check that what we were doing there, if we were safe and happy that we were succeeding in a test environment, we could take that to the hill climb and do it there. So we went to a place called Shelsley Walsh, which is the world's oldest hill climb, I believe, in the UK. It's very, very similar to Goodwood. It's very, very narrow. I mean, I think at its narrowest point, it's about 2.5 meters, and the car's 2 meters. So the localization had to really be there for that event. So we went there and we spent, I think, 2 or 3 weeks solid there, just doing run after run after run. So when we first get to a track, the first thing we'll do is we map the track. So we go out and we determine what is the drivable area. When you put a human in the car, as they're driving, they can see where they need to go. For us, we need to do that in advance to make a map of where we can drive. So that's the first thing we do when we go to a track. And then we start off super slow. So we go at 30 kilometers an hour, which is, just a bit faster than sprint speed. And we start there. We have a really, really low acceleration profile, so we're braking super early for the corners. We're not accelerating very hard out of the corners, and we slowly work our way up. And that was the aim of this event, was to go to Chelsea Walsh and find a set of parameters that we could put into the car which would be safe, that we could go to Goodwood and know that we could reliably set a time, that on every day of the event we could repeat and we could be within less than a tenth of a second every time. So that's what we did here. We started at 30 and we worked our way up, and eventually we got to 160 kilometers an hour on this track, which I'll show you what it looks like now. Yeah, that was cool. So that was testing complete. We'd gone to a track very similar to the one that we were going to. We completed a run and we'd fixed what we were going to do at Goodwood. And we said, even if every run that we do goes perfectly, even on that last day, we're not going to go any faster, because we're trying to show to people what we're capable of. And hopefully in the future, we'll be able to go and go faster again and again and again. But for the moment, the new goal was to go up Goodwood hillclimb at 160 kilometers an hour safely and repeatably every day. So for Goodwood, we were doing 7 runs. We were doing 2 a day for most days, and then on one day we did 1. And we had to make sure that we could do all 7 of those runs perfectly, because every single day there's going to be public there watching. They might only be there for 1 run. They might not be able to see any other runs. So if we mess up 1 run, then some people might go home disappointed. So we had to make sure that we could do it repeatably. And we felt, after going and doing our testing, we reviewed all of the data after the event, and we said, okay, we're pretty sure we could do this. So we turned up to Goodwood. I think we went for 11 days. Unfortunately, the track time wasn't great, so we were on track at 4 a.m. every morning for an hour, and then 9 p.m. every night for an hour. So we were getting less than 2 hours sleep a night, which wasn't great, but we worked our way up over the week before the event, and we were able to confidently say that we could do this at 160. When you're in testing, a lot of things come up that you're not expecting. I'm sure it's the same for anyone that's done any sort of testing. And the best thing you can do is fix that problem. The worst thing that you can do is you can't fix it. The middle ground is you can't fix it, but you can kind of live with it. And we use that testing to find all those faults that we could find, try and fix as many of them as we can, but those that we couldn't, we had to put a plan in place for if they happen during the event. So this isn't going to look like much to you guys, but this is our plan for that 60-second run at Goodwood. This is like 300 lines of planning. And it basically says, second by second, what's going to happen during that run. And if that doesn't happen, go to line 47 and do that. And if that doesn't happen, go to the next line and do that. And eventually, the bottom line is abort the run, which is obviously never what we want to do. But we're there to do it safely and put on a good show for people. We're not there to crash cars. So unfortunately, on one of the runs that happened, with Goodwood, as I said, timing's critical. You have to be in the holding pen, like, for us, it was 3 hours before our run was going to be, which meant that the car was just sat there for 3 hours in like 35-degree heat. Everything was overheating, everything was super hot. We sat there for 3 hours, we drove down to the start line, and on that drive down to the start line, our LiDARs are meant to localize, and we're meant to be able to figure out on that drive down where we are on the track, and it failed. We didn't figure out where we were. So we're in, another engineer called Alex and I were in race control, and we're inside, we're panicking, but we have this guide in front of us, and it says if this doesn't happen, do this, which was reset on the start line and hope that it works again. And that didn't work, unfortunately. And we have marshals on the radio screaming at us because we're on the start line and they want to go and we're not ready to go. I had Chip calling me. And we can hear Victoria in the crowd was with the commentators, and they're all talking about the car, and we can hear what they're saying, and we're panicking. But we have this plan, and unfortunately, we worked all the way down, and the next step was to abort the run. So we had to abort that run, unfortunately. We still put on a show, but we just drove the car up manually with one of our test drivers. But that was a real shame. But thankfully, that was the only one that went wrong. 6 out of 7 went perfectly. And I want to show you what happened when we went up the hill. So yeah, that was our official time at Goodwood. That was on the Saturday. We were part of qualifying for a shootout session, and that time was recognised by Goodwood. So we officially hold the record for the first and fastest autonomous car to go up the hill climb. And as I said before, we're really hoping someone goes and beats us, because we want to go back this year and have a time that we need to beat. And another company that we want to beat. So hopefully someone out there is involved and can put in a good word somewhere for someone to get involved, and we can hopefully go out and challenge for that. That was what we saw, what the public saw. I just wanted to show you guys quickly what the car was seeing during that time. Are being considered by the car for it to drive, to stay on the drivable surface, and then ultimately the blue line is the car's current heading. And this is what allowed the car to drive up that hill. The whole run was done just on LiDARs, and the software guys worked really hard to make sure that was going to happen well. And by the time that it got to that final run at the end of the weekend, all of us kind of had a relief moment where we were just happy that we'd made it. We hadn't had any big issues. We'd made it up 6 out of 7 times, and would manage to show on every day of the event really what we were capable of. So, as I said, the goal was achieved. We made it up the hill climb at 160 kilometers an hour. With the acceleration profile that we had, we actually wouldn't have gone any faster than 160. Hopefully next year we'll be a bit more, or this year even, we'll be more confident and we'll be able to push the acceleration profile a lot further. So you can see our time there, 66.96, which beat a few of the other cars out there, the human-driven cars, in their categories. We reckon we could probably go sub 60 seconds, hopefully next year with this car. And if we were to do it with that car, hopefully we could do it much quicker than that. So the goal, hopefully, is to go back this year and set another time that beats that time. And we're going to keep going and keep shaving time off every time that we can. So hopefully that gives you guys a bit of an understanding of what goes into running an event, what goes on trackside, and kind of the systems that we're working with to make sure that always happens safely. So thank you very much for listening. We're going to have a 10-minute break now for you guys to have some refreshments. Thank you.
Okay, everyone, it's Nikita Rushmanov for the second part of our presentation. Welcome, Nikita.
Thank you. Thank you. Thank you, Chip. So hi there, guys. My name is Nikita, and I'm a software engineer here at RoboRace /Hive. I'll tell you guys a little bit about myself. I've been a developer for 7 years now, and for most of those years, I've actually been a backend developer. But that's all born history. I'd much rather actually tell you guys about my darker side, which is drifting, and how I actually got hired here at RoboRace, because there's an interesting story about that. Coincidentally, I've also actually been a drifter for 7 years. Because the second I started getting my paychecks in life, I just started burning them, essentially. But anyway, here's my car. It's a 1993 S13 Vert. It's currently running SR20. Over the years, I've pretty much fully built it, and then some. I have a couple of other cars, too. I have a 1989 BMW E30 sedan that I also put an SR20 into, and you guys can actually find it way in the back of the hall there. It's parked over there. Yeah, it's a Nissan Transplant, exactly. And then I also have a 1986 AE86 Toyota Corolla GTS hatch. But anyway, so the story of how I got hired here, it really begins with my mom moving to New York for a year. And now you see my mom, bless her soul, she drives a C63 AMG. And, of course, you can guess what advised her when she was car shopping. But so she moves to New York for a year. And in all her glorious wisdom, she leaves the car to me to take care of while she's away. Yeah. So, so naturally, being the good son that I am, the first thing I do is I weld the diff. And of course, somehow I have to go and test out the diff to see if my welds hold. So I go, it's dark at night, I go find a tunnel, and I do a pretty fat burnout there, as you can see. Spulved it. Yeah. And so, my friend recorded the whole thing. He put it on Instagram. But in order to really connect the story, I have to tell you guys about Chris. So I have this friend. His name is Chris Marion, and he's actually the marketing representative of KW Suspension USA. And I worked with him on a couple of projects before, but so he saw the video of the bird, and he's like, cool, I'm going to send you some KWs for that car. And I'm like, cool, the car really needs them. It's kind of a boat. It weighs 4,300 pounds. But anyway, but Chris, he actually also happens to be friends with June over there, who works for RoboRace with us. So it's basically like the next day, and Chris and June are talking, and June is all like, oh, I'm trying to find more developers for RoboRace, but I want them to be like car guys too, and Chris is like, I know just the guy for you. So, he shows him the video of this burnout. So basically, the day after I welded the diff on my mom's car, I get a cold call from June, and I go through the interview process, and now I'm here telling you guys about this. The moral of the story here really is that you don't need a college education to get your dream job. You just need to weld a diff in your mom's car. So there you go. Yeah. But anyway, let's talk about self-driving cars. I think we can all agree that autonomous cars are coming, and when they will get here, they will basically revolutionize the transportation system as we know it. They'll ban people like me from the roads, obviously, which is going to suck, but that's all right. Yeah. Level 5 autonomy is kind of treated like humanity's next technological milestone. And because of this, of course, there's naturally a lot of big companies, working hard to try to get to this goal. And they're getting, billions of dollars in funding, and they're pouring all this doing all the development and research. They're pouring all this money into putting miles on these cars. But as you may have noticed, progress is slow. At least it's slower than people thought it would be. So, where are we at today? What are the problems these companies face? What are the challenges that they're trying to overcome? Well, building a car itself isn't particularly difficult. You can just take your normal car. You put a bunch of sensors on it. You give CAN bus control of the throttle, the steering, and the gas, and you put a big computer in it, right? Well, now you actually have to teach the car how to drive. And unfortunately, the neural network model that's running on a computer, it knows basically nothing about cars. In fact, knows nothing at all. It's basically like the brain equivalent of a newborn baby. And the government isn't too keen on letting children drive. So, how do companies get around this problem? How do they train this model? Well, they don't really, at least not in the way you think. They more cheat. So, what we can actually do is we can take this neural network model, and we can hack it up into separate, distinct layers. And by doing that, we can take each one of these layers, and we can train it in isolation without actually putting it into the real-world environment and endangering people. For example, you have the perception layer, right? The perception layer, you can just train it by feeding it millions of pre-labeled images, and you can teach it to recognize, cars, people, or traffic lights, Or you have the prediction layer. The prediction layer, you just record a bunch of vehicle data positions over time, and you just feed it that information, and it's able to basically predict where certain cars are going to go with a certain probability. The planning layer, you can just yell at it every time it draws a line through a curb, and eventually it'll stop driving through curbs. Or control is even easier. You just feed it a bunch of drifting videos and figures out what car control is basically from that. But so now you take these distinct pieces, and you basically hardwire the data flow between them yourself. So for example, you would take the perception output, which is just a bunch of vehicle position states, and you would feed that to the input of the prediction layer, which is going to take those vehicle positions and try to predict where the cars are going to go. And then you take those predicted vehicle paths, and you feed that into the path planning module, which is going to, based on where it thinks those cars are going to go, plan out your own route. And then you take your planned route, essentially, and you feed that to the control module, which is going to actually apply the inputs, the steering and the throttle inputs on a car to try to drive it along that line. Now, if you actually go and look at all the self-driving cars out there right now, you'll find that they typically have an architecture that is something like this. This is kind of a simplified example, but if you take a broader look, they resemble this in at least some way or form. But the reality is that unfortunately, this approach is actually somewhat crude, and I'm going to try to explain why. Now, you can actually just take this architecture and you can build a self-driving car out of it, but as these manufacturers put more and more testing miles in these cars, they discover that the world is a very dynamic place, obviously. But let's do an example. Say your car is driving along and you hit snow. What happens when you hit snow? Well, you have to change your driving habits, right? You have to drive more cautiously. But you see now, that little control module over there, it has no way of knowing that. Even though the perception module has cameras on it, it may be able to see the snow. Because we essentially hardwire these connections ourselves, there's no way for that information to get to the control module. Now, of course, you could say that you could take the perception layer, you could train it to try to predict the friction under the tire, and then hardwire that control module and have the control module react appropriately. But this is just one example. The reality is that there are thousands of different dynamic factors that occur in everyday driving, and we as humans just simply can't account for all of them and try to predict all of them. But you know what? This is actually what machine learning excels at. This is what neural networks do. The whole point of neural networks is that they're able to form connections that we simply can't predict ourselves. If we were just to take this architecture basically and try to eliminate all of the hardwired connections between them, and replace them with just free-floating neurons, then the network will basically, over time, as you train it by itself, learn to make that connection or association between the perception module and the control module. So that if the perception module actually sees snow on a road, the control module will by itself know that it has to drive more cautiously. The point I'm really trying to make here is that, with our current state of technology, in a lot of ways we're being forced to dumb down our neural network models, simply just because of our inability to train them properly. So, so how do we train that, right? Well, the only real way to train that is to just put it out into the real world and kind of let it learn through mistakes. But unfortunately, those are deadly mistakes. But let's think about this. So how do we train that network? Well, we could just try to simulate the whole world. How hard can that be? But if we're able to achieve an accurate enough simulation of the world, and if we can simulate all these dynamic factors that occur, in a real world, then we can train a much more powerful network. And not only that, but we can save these companies millions of dollars because on all the real vehicle testing that they have to do. So that's kind of actually the gist of what we're trying to do here at Hive. Here at Hive at RoboRace, we're basically building a decentralized vehicle simulation platform. That means it's going to be open source eventually. It's not at the moment, but once we have the platform in a bit more of a polished state, we do plan on open sourcing the whole thing and making it available to the public. But and of course, naturally, we're not the first people to think of this. There are actually a few platforms for this sort of thing out there already, but what we found is that they tend to be too narrow-minded. They make too many assumptions about the way things should be, the way car communicates, or the way your model should be structured. And in order to use their tools, you're kind of forced to conform. And this, this inherently stifles innovation because by conforming to these pre-existing architectures, you're left with no room to experiment. You can't innovate. So, a lot of the big companies out there that actually, have self-driving cars, they just end up hacking together their own simulation solutions, that happen to work with their architecture that they want to use, despite the presence of these already developed open source free tools they could be using. So what we're really trying to do here at Hive with that platform is we're trying to overcome all of these restrictions so that any entity out there would be able to use our platform, basically, in the way they need to. And while we do currently mostly focus and cater, currently mostly focus on catering to autonomous vehicle research, we're developing this platform in such a way so that it can be used for a variety of tasks, such as like your engineering simulations, or if you're trying to build a game for a racing simulator. Basically, any vehicle simulation need can be met. Really, what we're trying to build is much less of just like a simulator program for you to use, and more of a whole simulation ecosystem that you can configure, for your own use case, or and modify as you need to, essentially. So let's talk about networking a little bit. I know it may seem like a boring topic, networking, but it's actually one of the hardest things to get right with what we're trying to do. And the reason for that is because networking determines how all of the modules in your simulation on your car communicate. So the networking protocol that you use, in a lot of ways, drives the architecture of your application. And going back to some of the already existing simulation platforms out there, one of the biggest restrictions that they tend to impose on you is actually the networking protocol. And this sucks, because let's say you want to use this new, or you built your own custom networking protocol that can have has less latency, so your car can have like a faster reaction speed or something like that, whatever. But the simulation tool you use is already designed around a different networking protocol, and you can't just interchange them that easily. Well, now you're just kind of stuck. You have to develop your own platform or something. But so here at Hive, really, one of the most important things we're working on is we're trying to create an abstraction for the networking protocol. So what that means is that basically, in our platform, we avoid ever using these networking protocols directly. Instead, each module communicates through an interface. And I know a lot of you guys here aren't software people, but so what an interface basically it allows us to have is a swappable implementation. So what that means is basically our platform is able to be used with a variety of different protocols, just by changing the configuration files, as simple as that. And really what we're trying to do is we're trying to define and use interfaces for everything. And it's really kind of funny to talk about this because it's such a weird software thing, but really what it just boils down to is having good software design principles. And this is kind of why we're really spending so much time and care developing just the most basic core part of our platform. Because if it's wrong now, it'll essentially be wrong forever. So the core of our platform is basically the component system and a data system. The data system, as I mentioned already, is basically going to provide us abstractions required to be able to use all these different networking protocols. And the component system basically enables us to swap out different implementations of all the modules running on our platform. So let's say you're doing like an engineering simulation, right? And you're testing how a car responds to a certain road scenario. Using the component system, you would be able to swap out different tire models on the fly, or you could try using a different suspension software to see if the car reacts differently, or something like that. Now, this sort of robust component system, that actually allows you to swap out these modules, is incredibly important for autonomous driving development. Kind of let's face it, basically, if you're building a self-driving car, right, you're going to be doing large-scale simulation, and because your neural network model is pretty much going to need to drive millions and millions of miles to be able to learn anything. So you're pretty much going to be running your simulations in the cloud because you don't have another choice, essentially. And of course, if you try to run these simulations in real time, it will take an incredibly long amount of time. But more importantly, it will cost you an incredible amount of money in server costs. So using the component system, one of the things you could do, for example, right, is you could stage your training in the cloud in such a way so that at the beginning of your training cycle, the simulation runs at 1,000 times faster than real time, say, And you could do it very simply just by changing the physics implementation or the rendering implementation for much more computation, for much simpler implementation that's, easier on a computational resources, but it's not as accurate, of course. Because at the beginning, it doesn't really matter, when your network is untrained, it doesn't even know what a car is, it doesn't matter, like, if your suspension geometry is not being perfectly simulated. The network just needs to learn what driving even is. And then as your network matures and actually learns how to drive, you can incrementally, like step by step, swap out these implementations for more intricate ones. And your simulation speed will, of course, slow down a little bit, but now your neural network model can essentially refine its knowledge and learn the deeper intricacies of driving, for example. So the component system proves to be a very, very important tool for controlling your training speed, essentially. And having this fine-tuned control over the training speed of your AI, basically it just allows you to train faster and cheaper in the cloud. Another topic, rendering. Rendering is really important for autonomous driving development. Because let's say you want to build a network or something, an AI that can recognize certain objects from a simulated rendered camera feed, right? Now, if you want to take that network that you just trained and be able to use it on a real camera feed, the rendering that actually trained that network has to be incredibly photorealistic. So here at Hive, we've had a lot of debates about different rendering engines, and at the end of the day, the only thing we could really all agree on is that nobody really knows which rendering engine will be the best in 2 years. So because of this, we're very much afraid of tying ourselves to any particular engine. So you guys remember how I said, interfaces for everything, right? Well, and of course, we also have an interface for the rendering engine. And this is not only because we don't know, we can't predict, as render technology develops, which engine is going to be, become the most photorealistic or, the one most useful for your AI development. It's actually also because there's a certain secondary benefit to being able to render in multiple engines at once. The way machine learning works and neural networks work is as they learn, they like to cheat a lot. They have a tendency to learn the behavior of artificial artifacts in the data you feed it, instead of actually learning their inherent logic that it needs to know. Like an example is, let's say you're training a network to, recognize people from a simulated camera feed. It could very easily just learn that if it sees a pixel of an exact color that just happens to match the skin tone of the human model you used in your simulation, then they go, that's a human. But it doesn't actually teach it to recognize faces as human behavior. It just associated a color code with a human. So once you put it out into the real world, it just falls apart. But now, let's say we're able to feed it the same camera feed, but from 4 or 5 different rendering engines, right? Well, now the network can't rely on just learning these artifacts because each engine is going to have different artifacts inherently. So in a way, having multiple rendering engines at once almost serves like a filter to be able to force your network to learn the intricacies of the problem at hand. Another way neural networks like to cheat is actually the same way students cheat. They just memorize all the answers ahead of time. It's a lot easier for your neural network to just learn that, you just make a left there, right there, and then bam, you've arrived at the destination, than to actually learn the intricacies of navigation and control. So in order to actually force your neural network to learn the problem space at hand, you have to feed it an incredibly large amount of different locations to learn on. You can't just have it driving around on that one map, because then it'll just learn how to navigate on that one map. So this is where our Ribbon project comes in. The goal of Ribbon is basically two-hand. One is to be able to procedurally generate locations and assets out of thin air. And two is to be able to generate these locations and assets, but from captured data, so like LiDAR data or camera data or GPS data. The first goal is really useful for AI development, of course, because it gives you the ability to generate an infinite number of scenarios to train on. And the second goal is really useful for validating both the AI that you trained on that and actually validating your ability to procedurally generate these tracks in the first place. And look, I'm not going to lie, this is actually like an incredibly difficult problem to solve because you're essentially trying to generate a whole world, through code dynamically, which sounds impossible, and it is. But at RoboRace here, thankfully, we mostly deal with race cars, so this makes things way easier because we only really have to generate racetracks, and that's the only reason it's even possible. Because racetracks they're stupid simple compared to the actual complexity of real streets, which is the only reason we can do that here. But anyway, that's all I have for you guys. Oh, actually, no, we do have a demo for you guys. Like I said, we're still very early on development, and we're mostly working on our core architecture. But we're going to showcase you some of our capabilities so far. You're going to see basically some of our networking progress and some of the abstractions we have already. But anyway, let's go over there, guys. I'm going to take us over there. We're going to have a demo for you guys. Let's go. Excuse me.
I'm pretty sure that's a cricket. Hey, good job. That was a great presentation.
Oh, thank you. Appreciate it. Matt, you want to fire it up?
Yeah. Is everybody else ready?
Presumably. I don't know.
Just fire it up, start running.
In theory. In theory. So, have any of you guys ever heard of R Factor? Okay. So, for those of you who don't know, R Factor is a very old racing game. And it's actually kind of funny because a lot of modern racing titles have the code base based on the R Factor code base. And so we also actually license the code base and we use it as our baseline physics implementation. So in this demo, basically what we'll have is we have Robocar being driven around in R Factor, well, our own version of R Factor, with R Factor's physics. And in a process, it's being networked essentially to 3 different rendering engines. So we have Unreal Engine 4 here being able to render R Factor, being able to render Robocar as it's being simulated in R Factor. And then we have Godot over there on the laptop, which is also doing the same thing. And then we even have our own viewer based that we just use for testing that's also being able to render the same view. So, what this demo is trying to showcase basically is that we're able to completely abstract the rendering engine and at the same time we're able to use multiple rendering engines at once to be able to acquire as much data as we can. Oh, he's going to hit it. Watch this. That was DevBot. It's just on track for some reason. I don't know. But anyway, I think we have a Q&A now, guys. If you'd like to go back to the stand for Q&A, let's go. Back to the seating for Q&A. Yeah.
Q&A. I've got just a few other things to say, so just
Sure thing.
call me up when it's all over.
Okay. Absolutely.
I think time-wise, I guess we only have 8 minutes.
You tell me.
You probably do.
You know what? When you feel it,
Yeah.
just come up,
Yeah.
and
Just
we'll
end it
go
right
from there.
there.
Yeah.
All right. Sounds
Exactly.
good. Cool.
Let's see if we'll do this.
All right, I'll take a seat.
Okay. Are you still mic'd? Should be able to, yeah. Folks, we have time for I know a lot of information. Thanks all for your patience and your interest. We have time for a few questions. So I look at all the questions. Why don't we start right here? He technically was first.
Instead of getting in a very generalized discussion in terms of all the technology you're working on, you talked about your various interfaces and everything, and you're all doing this through computers. If you could take any part of your technology, be it sensors, be it processing, be it whatever, and if you could make it, say, 100 times better, which piece of technology would you want to improve the most?
Just for everyone, the question is of the entire toolbox we have, which piece of technology would we like to improve the most?
Rendering. Yeah, that's the one. Because you can.
But is that the hardware part of that, or exactly what are you trying to do?
It's both. It's about being able to. It's not just rendering. It's really. Damn, it's more complicated than I thought. Because.
I was trying to think all that, and I realized it was going to be
Yeah. Well, the real. Like I said, honestly, the biggest challenge, as I was mentioning, is the ribbon project. Actually being able to recreate the real environment, the real world environment fully. And part of that is rendering, but part of that is also being able to actually generate these assets. So a lot of it, I think, it's a mixture of being able to render them and generate them. So it's kind of like a whole pipeline that requires improving. You have to improve the hardware. You have to improve your software abilities of rendering-wise. You have to improve your data capture abilities. And you have to improve your AI that can actually generate these assets, too, in the process.
So in a sense, you would do that first rather than trying to work on any of the controls aspects?
Well, because the controls aspects, they're just closer to being let's say 90% of the real thing, right? Whereas rendering is like 30% of the real thing. So the gap that you have to fill there is much bigger at the moment.
Thank you.
Thank you.
Yes, sir.
So what is the revenue model for the company? Is it selling cars, is it sponsorship, is it something else?
Yeah, so good question. The question was, what is the revenue model for the company? And right now, we're clearly in the investment phase. But what we do is as we ramp up with teams, the teams pay a fee to race. The commercial teams also buy a franchise. So a pretty traditional model that way. So the franchise fee basically gets them invested in the series. If the series takes off and it gets bigger, their value of the franchise goes up. In addition to that, they pay an operational fee each year, and that operational fee helps defray our costs. Over time, the revenue model is we look for RoboRace to grow. We look for the championship to grow. That, of course, will start to accelerate once there are actually autonomous driving systems that are available to the buying public. At that point, you'll have manufacturers and you'll have tier ones, and they'll need to differentiate their product from other products. And that's the platform we're building, is a platform for manufacturers to be able to differentiate that their autonomous system might be better than their competitor's autonomous system. And that really changes the game with regards to the economics of it. Because then we become a marketing platform. So that's why we're working on our media and having a big audience in place for when that time comes. But that time won't come for what's the horizon on that is whenever we get to that point where you're going to be able to have your choice of autonomous systems in a car, and maybe that's 5 years. We don't know yet.
So your version of Race on Sunday is selling?
Our version of Race on 2020 sell in 2025. Yes. I think we had one over here, sir.
My question is, how are y'all working with competitors to start building these cars, and what kind of regulations are in place once y'all start having this competition?
I'll start off on that, and maybe Matt has something to talk about with that. So we are obviously we've done 2 cars so far. We have the Robocar here, and we have the DevBot 2, which you saw in the videos. And both of those were done for specific reasons. We're in the conversation phase of what our next vehicle will look like, and that is a product of constantly learning and figuring out what do the teams need, what's the right economics for the car. In other words, how much does the car cost? How much does it cost to crash the car? How readily can we change sensors on the vehicles? So it's something that we're constantly looking at and trying to come up with the right solution for the right platform when we get to that time when we have something that will work for everyone.
I guess my follow-up to that is like if for a company were to try and start building their car to compete on your stage, what is the cost of entry for that company?
So right now we provide all the cars, and there's a very specific reason for that. We want the companies that are competing within RoboRace to have their focus on the software stack. We want their investment to be on the software stack. We want that to be the point of differentiation. We don't want the car to be the point of differentiation. Also, I won't tell you how much it costs to develop this car here, but it was a lot of money. And if we asked every manufacturer coming in to develop their own car, I think it would be a huge hindrance to the series. Developing their own software stack is work enough, and that's where we want their efforts to go. And that's why, related to your first question, we have a very open discussion, ongoing discussion with our partners, with our teams, about what they're looking for in a car and what works. And then we need to make sure that works with what we're doing as well. Does that answer your question?
Sort of.
Yeah. It's just to put it bluntly, this is a series about autonomous software, and we don't want the first hurdle to enter is to go out and spend 10, 15, or $20 million developing your own car and then starting to worry about the software. We'd much rather you just focus, our competitors focused on the software.
Why do you have a steering wheel in the
Yeah, great question. Matt would love to take that one. Yeah.
So well, the real reason is that this car is a development car. So it's drivable by a human. We can put a guy in and they can drive it. We can put someone in and have them driven by the car, or we can have no one in the car and have it drive itself. It's really important, one, just for a race car development point of view, to have it drivable by humans, just to shake the car down. If we strip the car, rebuild it, for example, we just want to check everything over without having to run it autonomously. And then also we put a guy in there so that they can, if they need to, they can take over if there's ever a problem. So we have a safety driver in the car when we're first developing new software. So for example, this is something that we've had. We'd be going down a straight at 100 kilometers an hour, and all of a sudden the steering wheel's just gone 90 degrees right out of nowhere. And if we didn't have a human driver in the car would have gone in the wall, and that's an expensive bill for Chip. So that's the real reason. And also, it looks cool when there's no one in it, and you can see the steering wheel going around by itself pretty much. So yeah, that's it.
So for 2020, you've got the beta series, and then 2021 you've got series 1. So if I wanted to be an entrant, how would what's the process of doing that? What's the cost of getting the car?
See me immediately after this Q&A. The process is it's definitely a consultative process. We're constantly talking to organizations and teams that are interested in being a part in RoboRace. So we begin the discussion and figure out if the organization has the right skill set and wherewithal to take part, and it's really an information sharing at that point. There are a couple different ways to enter the series. and it's actually for our first couple teams. It was an arduous process. It was a long process getting them integrated into getting their software integrated with the hardware was a process. We've gotten a lot better at that. We've worked hard on our documentation and also our process. So we have a series of quality gates that the teams go through, and I think that Graz came through from first test to competing was 6 or 7 weeks. So 6 or 7 weeks and probably 10 on-track days and a lot of simulator time.
Is it in any way a traditional race team, or is it a software business as a competitor?
As a competitor, there is, it's a good question. It's software, but there's also vehicle setup. Coming in and maximizing the vehicle, it's similar to traditional racing where we begin and you start with a setup sheet, which is 80% of that setup sheet would look like what you would expect as a racing engineer for any car, internal combustion or self-driven or human-driven.
So as a competitor in the series, does everyone get a map for their car? You know, so if you have 10 entrants, do you have 10 maps?
Yes. Yeah. Thank you.
Quick question. How do current racing legends, best current Lewis Hamilton, feel about this car? Not necessarily taking their spot, but how do you see them reacting to the whole thing of autonomous racing? And do you see them kind of being involved in it?
So the question was how do current racing drivers feel about this? I answer that question from current racing drivers quite a bit. So one of the questions, and this goes back to your question of why was there a steering wheel, one byproduct of it is that we can also always gauge the performance of a software stack against the best human drivers. And this is a very interesting topic for us. And we're very close to approaching the point with the DevBot to where the software stack is going to be quicker than a human driver, believe it or not. So we can take the exact same car and the same conditions of the track. The human driver goes out, sets their fastest lap, and then the human driver gets out and we have the software stack take over. We're not there yet, but we're getting close and we're working hard. We're working hard to achieve that, but we believe that's within a near term. It's a near-term goal for us.
So essentially like consultants.
Yeah. So exactly. So what happens is you get different types of teams, and there's nothing better than having a professional driver sit down, take a look at the data trace, and say, hey, your software stack is giving up time, just as you would with a teammate on a two-car team. You might compare data and see where you're dropping some time. It's the same thing with the AI and the human driver. Vice versa, the AI now sometimes can show the human driver where they might be able to go a little bit quicker too. But the AI has a little bit of a cheat because it has more control surfaces than a human has.
From a fan audience perspective, longer term, do you see competing with existing forms of motorsport, or do you think it creates new audiences?
Another good question. We've decided internally we're not trying to change the minds of people that love motorsport. When we do things, we see the comments on social, and they're like, "Oh, but I love my driver, and it's not real without human drivers, and it's all going to be the same." And the way we feel about that, we're looking for a wider audience. Again, we're looking to tell the world about autonomous. So engineering audiences, tech audiences, gaming audiences, which are very big audiences, are very important to us. So we don't look to speak specifically to anyone, but we're not trying to change the minds of motorsport. I think that will happen someday when we have 10 cars going down into a corner, fighting for the lead, and it has to look more spectacular than what they've seen before. Then and only then will they then come over. So Matt and Nikita will keep working to make that happen, hopefully in the next couple of months, right guys? Yeah. Sir?
Yeah, to follow up to that, when do you see, I mean, have you run, besides Goodwood, anything in front of spectators, like any of the head-to-head battles, or is that, private test environment as you're developing your software? And when do you see it go into spectator?
We've done it kind of in private, not because it's a secret, but honestly because it's a little bit boring right now. Our safety margins are quite high. We, as Matt showed you, the long list of tasks we do. If you were sitting in the stands, you would watch a car go around, and then we'd go away for 2 hours, and then we'd come back out and you'd watch some cars go around. So a big part of, while we're developing the software and we're developing the performance and the precision of the vehicles, we're also developing the entertainment product. So that's what Goodwood was really good at. Goodwood, at Goodwood, they say you're on at 10:16 a.m. and you have to track from 10:16 a.m. to 10:17 a.m. and you have to hit that. You have to hit that window. That's a big challenge for us, and that's what we're always working on. It's one of the things we work on. So that's why we kind of do it in private. But this year and this season, we see our audiences much more being audiences that are out there on the internet. So we will be live streaming. So it won't be, again, there are no secrets. We're going to fail. We're going to crash cars. All these things are going to happen, but I think it's really important for people to see the process so that there's a belief that this is real and this is how we make our progress. Sorry.
Just to clarify, would you characterize your business as a testing service? In other words, you service a clientele that wants to try out their own skills and software? And is that clientele simply people that are interested in racing, or do you deal with large auto companies, General Motors, Toyota, etc.? And secondly, you see your final achievement to promote autonomous vehicles for the public in general, or are you really just focusing on racing?
I'm going to take the last part first. The final achievement is to promote autonomous vehicles in general through competition. And who knows, in a couple of years' time, our competition probably won't look like our competition does right now. And it probably won't look like a traditional motorsport race. We look to go into areas that we feel are more relevant to everyday road drivers because of what you mentioned. What was the first part of it that I?
Was that just inquiring about your business and what is your clientele like? And whom do you?
Are we a testing service? Yes. So in a way, yes. I think that each one of our 5 teams is probably in the sport for a different reason. They're all testing things, and each of them have different focuses of what they and different areas where they excel. That's one of the interesting things that we're always dealing with. But we presented the competition and some of the competitions that we did, like at Monteblanco and the demonstrations at Goodwood. But that's kind of just scratching the surface. We also have special projects that we do with major manufacturers. And you can, some of them are obviously confidential, but you can see some of them on our YouTube channel as well. So where they come out and they have something very specific that they want to delve into. They have an idea, they have a concept, they have a group of software engineers, and rather than going out again and building their own car and going through all this, we're a very convenient platform for them. We have the car, we have the engineers, we know how to do the integration, we know how the cars behave on the limit, so we give them a very easy way to plug in, come, do their tests, have the learnings that they need to do, rather than making it a whole internal project for them.
Well, would you ever make available something, just a dumpy little sedan that goes through an obstacle course?
Dumpy sedan, probably not. But we are, as I said, we're thinking about next generation vehicles for us, which they'll be very, very fast and very exciting, but they'll also be more road relevant. Yes, ma'am.
Do you see any similarities to current Formula One racing where there's a pit lane, they have to come in and change their tires, get recharged, that sort of thing, a variation instead of just going around and around and around?
I'll let one of our resident Formula One fans take this, yeah.
Yes.
Yes.
Essentially. One thing that we're actually working on at the moment is implementing a pit lane. So at the moment, if we want to run a race or some sort of testing, a human has to drive the car out of the pits, do an outlap, and then stop on grid, get out, come back to the pits. One thing that we really want to implement is that the car drives itself out of the pits, into position, launches itself, goes from there. So that is definitely something that we'd be looking to implement. I don't know if it's necessarily taking stuff from what is Formula One, but it's just stuff that is more realistic for us to be able to test efficiently and try and remove humans out of it as much as we can, because it wastes time and we kind of have to put more effort into that side of it. If we could just set it up that we sit with the car next to us in the garage, we press a button, it goes out and drives and tests and comes back, then that would be...
If the car gets a flat tire, someone's got...
For sure, we have full race teams that come to tests. It's potentially that's a question for Chip.
The moment they're faster,
yeah. Yeah. So yes, essentially we will be doing stuff like that for sure.
How many people work here?
Yeah, so RoboRace is a relatively small team. RoboRace is about 30 people. So here in Los Angeles, we have, on the software side, about 15 or 16. And then we have operations happening in Las Vegas and then in the UK, and then also the executive offices in London. So we're busy. Yeah. Just maybe time for a couple more questions. Yes, sir.
As you put together, right now you've got essentially 5 entities that want to play with you. How much pushback do you have in terms of defining the interfaces between what they're supplying and you? I can imagine that might be, some would say, I'd like it a little bit different. How are you playing that?
Yeah, I mean, there's always a discussion, and so far it's been pretty good. What will happen is as this gets more competitive, it'll get harder and harder and harder. And the project to date has been kind of a project of we're all headed in the same direction and we're trying to achieve the same thing. But we're seeing it. We're seeing it in the off season already. It's becoming more competitive. There's some challenger teams now, and now there are a lot more questions. No, I was writing an email till 1 a.m. this morning regarding this topic to a team. Any other questions? Sure.
Yeah, at this point, the car's fixed and everybody's just working on software. But it seems like the sensor technology is still evolving, and people have different ideas about that. Maybe some of the people who are interested in entering, that's their part of the business. Do you see it opening up? Because somebody's going to want to maybe redo the sensors and the way the car sees the world.
Absolutely.
Maybe.
The sensor stack is going to be a proprietary element of everybody's system. So in our next generation, we see the sensor stack being much more open, to where a team can bring whatever they would like within reason, as long as it fits within a box, within a parameter. In season alpha, we had the team I was talking about, TU Graz, out of Austria, and they joined. And as they were getting up to speed, they wanted to bring a different type of LiDAR than what was on the car. This car has several LiDARs positioned around the car, and they wanted to bring a 360-degree LiDAR that sits on top of the car. And from a rules standpoint, it was something we had to look at, but we talked to the rest of the teams, and we felt that it was something we were curious about and we wanted to learn about. And we don't ever at RoboRace want to stand in the way of innovation. So we allowed it, and coincidentally, the last race of the season they won on that sensor.
So not just software.
Yeah. It's ultimately it's got to be the whole package. We see the sensor stack as being a big part of it, though. Last question, sir.
Now, would you kind of going along the same thing, like in the future, would you be saying like maybe if because a lot of this stuff is very computationally intensive, to where if teams have hardware that they want to bring in the loop. So let's say we have this, we got this super computer that we want to use to basically run their software on their hardware and then interface your vehicle. Is that something that may happen down the line?
We should have stopped at the last question. This is yeah, exactly. It's an open question for us right now. Right now, per the rules, no. But I don't know if either one of you have specific thoughts on that topic.
I think as we progress in future seasons, then, as Chip was saying, at the end of the day, that's a part of a kind of sensor package in a way. So I think it may get more open as we progress, but for the moment, that side of things is locked down. But it is something we're discussing.
One of the things we look at, and probably the best way to answer that is a technical roadmap. So as we have larger organizations and larger companies that are looking at getting involved in RoboRace, they want to know where we'll be in 5 years. And honesty is a really, really hard question because it's moving that quickly. I don't know how familiar you are with Formula E. Okay, so very similar to Formula E's technical roadmap, which had 2 major changes in it as they learned more. But essentially, when you started in season 1 in Formula E, everyone was running the same car, the same inverters, the same batteries, the same motors, and then they started opening it up. We see the same progression happening with RoboRace. We're totally open to this. Well, I'd like to thank everyone, and thank you all for the great questions. Really, really, really good questions. I would be remiss if I didn't recognize 2 people before we close. At the back of the room, Michelle Villanueva. Michelle, please wave to everyone. Thank you. And just behind Michelle, June and I. June was actually the one that worked with SAE to make this whole thing happen. So thank you very much. And we look forward to continuing our relationship with all of you. You're always welcome. And we hope to do this again sometime in the not too distant future. And to answer some of your questions, we will work with SAE to get an invitation out to one of our events and see the cars if you're at all interested. As I said, we're open. 2 more housekeeping things. At the back of the room, we have gift bags with something that's very special for us. It's the Robocar Hot Wheels in it, and it is a limited edition one. It's in a collector box that has a hologram on it, and each one of the Hot Wheels vehicles has been signed by Daniel Simon, who I think some of you met this evening. He was the designer of the Robocar. He also did the surfacing on the DevBot too. So if anyone didn't have a chance to get on the VR rig, we have time for a few more VR rig rides, and then we also have our simulator running in the back. We'll stay around for a little bit longer if anyone wants to try that. But thank you very much. Drive safely. Watch out for the human drivers out there, and we appreciate your time. Thank you.